Alright, so today we are talking about the hyperbola. We're just going to remember that it comes from a cut from a double nap cone, and the hyperbola is going to cut through and make two sections, two curves, two disjoint curves. They're not joined, they're not connected, because you have this vertex separating there. So, much like we had the parabola that could open left or right or up or down, and then we had our ellipse that could have a major axis going horizontal or vertical. When we get to the hyperbola, there's two types. So we're going to start with one that opens left and right, a horizontal hyperbola. I'm going to come in here and make a coordinate plane. You want to make it kind of big, like not whole piece of paper big, but pretty big, because we're going to put some vocabulary all around it. Alright, we're going to come in here and draw some dashed lines that make an X. So these are asymptotes. If you remember, an asymptote is like a boundary line for a graph. A graph gets closer and closer to an asymptote, but it doesn't touch it. When we graphed our tangent functions, we had asymptotes because that was a place where tangent was undefined. So our hyperbolas approach asymptotes. So we're going to draw a hyperbola. Where these asymptotes intersect here, this is the center of your hyperbola. And the center is HK, exactly like the ellipse. So, that's nice. And we have a vertex here, and another vertex on the other side, and those vertices are same distance from the center. And then you'll have a focus point here, F1, F2. So your hyperbola curves towards your asymptote, getting closer and closer but doesn't touch. And then over here it curves towards your asymptote and gets closer and closer but doesn't touch. And then on the other side, same thing, we curve towards the asymptote but don't touch it. And then curve towards this asymptote but don't touch it. Every point on the hyperbola has a special connection. So if you remember with the ellipse, every point on the ellipse was the sum of the distance from the focal point to that point and then over to the other focal point. The hyperbola, it's the difference between those distances. So think hyperbola is going to go with subtraction. Hyperbola is going to go with subtraction. Now, on our ellipse, we had a major axis and a minor axis, and it would have been really nice if they named the hyperbola the same, but they didn't. So on a hyperbola, your axis that touches the vertices, so this guy right here in my brown colored pencil, that is called the transverse axis. Now, the distance from the center to the vertex is A, just like it was on the ellipse. So the length of a transverse axis is going to equal 2A. So in my mind, I like to think of the transverse axis that it is like the major axis. Because to me, the major and the minor axis in ellipses, that just makes so much sense. So if I can connect that in my brain, the transverse axis, it's kind of like the major axis because the two vertices are on it. The reason that it's not like the major axis is it doesn't have to be the longest. So that's probably why they don't call it major and minor, because it's not necessarily the longest. The word transverse, trans means to move, like transportation. So it's the axis that moves between the two vertices. Right? It goes between the vertices, transverse. The other axis is called the conjugate axis. And the length of your conjugate axis is equal to 2b. But where even is that conjugate axis? So here's what happens with the hyperbola. You go from your vertex up to where you intersect the asymptote, and that makes a 90-degree angle. And so you get like this little box that happens. So the vertex up to the asymptote, turn the corner. So this right here is a conjugate axis. So your B is that little part of the rectangle. So we want to talk about this focal point here. So remember, plural for focus is foci. And so letter C, like the ellipse, it's going to be the distance from the focus to the center. And like the ellipse, it has to do with the Pythagorean theorem. But this time, the A is a leg, and the B is a leg, and so the C is actually the hypotenuse. So it actually is exactly the Pythagorean theorem that we're used to. C squared equals A squared plus B squared. So that's how you're going to find the foci. All right, so then last but not least, let's look at the equation. The equation for this hyperbola is x minus h squared over a squared minus y minus k squared over b squared is equal to 1. So first you look at, Ms. Collier, isn't that the same equation as the ellipse? Almost. What's different? The minus. All right, so then let's just talk about what if our hyperbola opens the other way. So I'm going to quickly draw a coordinate plane. I put in my two asymptotes. I'm going to come in here and draw that box. So here's my vertex. I go out to where my vertex intersects my asymptotes. I have this box-like situation going on. So my A, so this time the transverse axis is vertical. Now remember, on an ellipse, A goes with the major axis, and A is always the longest. A doesn't have to be the longest on the hyperbola. But there's A, and then this distance here on my conjugate axis would be B. So how is that going to change the equation? So think about subtraction. Order matters in subtraction. So the key thing about the hyperbola, whichever way your transverse axis is going, that letter has to come first. So since this is a vertical transverse axis, the y has to go first. So it's going to be y minus k squared. The transverse axis is going to have the letter a, so that can stay a squared, minus x minus h squared over b squared equals 1. So, if you compare the two equations, the difference is which term goes first and second. And your leader is going to be your transverse axis direction. So, your transverse action is horizontal, you lead with x. If your transverse axis is vertical, you lead with y. Now, there's a connection here with the A and the B and these asymptotes, right? The asymptotes can be slanted different ways, and so the A and the B have to do with slope. So here's my center, here's a point on my asymptote. How do we find slope? Rise over run. So the slope of my asymptote, isn't it A over B? Rise over run. A is my rise. B is my run. I know some of you are trying to write and look at the same time, so just pause a minute and look. So I'm right here. This is a point on my asymptote. I want to get to this point on my line. Rise A, run B. See how it rise A, run B. Rise A, run B. That's going to give me the slope of my asymptote. Rise A, run B. Alright, so for our practice about hyperbolas, we're going to practice two things in IXL. P10 is going to ask you the properties. It's going to ask you about your transverse axis and your center. And then P12 is going to ask you about the equations. But guys, for both of these, we only need the SMART score to go to 50. We're really just dealing with the introduction to hyperbolas. So you're only going to 50.